And now we have just a quick video to look at the actual arrangement of electrons around the nucleus of an atom. So when we talked about atomic structure, talked about how in the nucleus we have our protons and our neutrons, and the electrons are sort of buzzing around outside. It turns out that there's a pretty precise arrangement to how those electrons are arranged, and that arrangement actually ends up giving rise to the vast majority of properties that an element will have. It'll dictate how that element bonds with other elements, and then ultimately leading up to some of the properties of the compound that results from that. And so this is a fairly important just concept and some fairly important ideas here that will really help us to discuss how elements behave when they react with other elements. And so electrons, we do have to note, have energy. And the electrons can only exist on certain energy levels. Think of it sort of like unevenly spaced steps. And so here we have, and so this is a good drawing of it here. Here we have our nucleus here in the middle. And we can think of these energy levels where the electrons exist as shells. And so here we have one shell here. And so we can find electrons here on this shell. And we have shell 2 a little further out, shell 3, and shell 4, and so on. And the reality is a little bit more complicated than this, but we're going to simplify it a fair bit for the purposes of this course here. Electrons will not be found except for on those shells. So you're not going to find electrons here between the nucleus and the first shell. They're just not going to be there. You can find them on that first shell. You're not going to find them in between here, in between the first two shells, but you will find them here out on the second shell, and so forth. And there's a couple different ways you can think of this. Again, it's not a perfect analogy because the reality is very complicated, but you can almost think of it like a solar system, and that's one of the analogies used fairly often for this model, is that here's our sun in the middle, and the electrons are similar to being seen on the planetary orbits. You know, you don't see a planet, you don't find a planet in between the sun and Mercury. It's just the sun, and then you get out to Mercury's orbit. Similar sort of idea. And if we think of it also as sort of like rungs of a ladder, you know, you can step on one rung, you can step on another rung. If you try to step in between, something bad going to happen. And so it's kind of a similar idea, that electrons can be found on one rung, they can be found on another rung, but they're not going to be found in between those. Each energy level, each shell, we denote as n. So like n equals 1 is the first shell, n equals 2 is the second shell, and so on. Each of those energy levels can hold 2n squared electrons. So the first energy level can hold 2 electrons. 1 squared is 1, times 2 is 2. Second energy level, 2 squared is 4, times 2 is 8. So the second energy level can hold a total of 8 electrons. Third energy level can hold a total of 18 electrons. Fourth energy level can hold a total of 32 electrons, and theoretically, going on from there. Remembering that atoms, for now, we're going to mess with this in just a little bit, but neutral atoms have equal numbers of protons and electrons. And so we're able to figure out how many electrons an atom has and how many are on each shell by knowing what type of atom that it is. Electrons will fill up in order of their energy level. And so electrons will first go to the first shell until that's filled, and then out to the second shell until that's filled, and so on. For the first 20 elements, we fill the energy levels with 2 electrons, then 8, then 8, and then 2. I realize that this doesn't necessarily coincide with our 2n squared. It does for the first 2. You know, our first energy level holds 2, our second energy level holds 8. Our third energy level technically holds 18, but we actually start to go out and fill a little bit on the fourth before we completely fill this one up. Don't worry about the reasons for that. Those of you who possibly eventually go on to CHY 113 and some general chemistry, you're going to see the reasons for that. But suffice to say that what we talk about here in this course only scratches the surface of what's really going on with electron arrangement. It's much, much, much more complicated than this. We just don't need to get into those complexities for what we need to know in order for this, to learn what we need to know for this class. And so just know that yes, the third energy level can hold more than 8, but we actually only put 8 in there before going on to put a couple in the second, or sorry, in the fourth energy level, in the fourth shell. So that sort of looks like this. So for instance, a calcium atom. Calcium right here on the periodic table, atomic number is 20. 20 protons in calcium's nucleus, 20 electrons in a neutral calcium atom. And so those 20 electrons, we can find 2 here on the first shell. We'll find 8 out here on the second shell. We'll find 8 out here on the third shell. And then we'll find 2 out here on the fourth shell. The very outermost electrons are what we call valence electrons. And in fact, we call that whole shell the valence shell. So here with calcium, we have these 2 out here on the fourth shell. This fourth energy level is called our valence shell. And these 2 electrons that we find out here, these are called valence electrons. All other electrons are known as core electrons. And so these other 18 electrons here in shells 1, 2, and 3, those are all core electrons. And again, with these outer ones called valence electrons. This is one of the ways the periodic table is set up. Main group elements that are in the same family, that are in the same column, have the same number of valence electrons. And so hydrogen, 1 valence electron. Lithium, 1 valence electron. Sodium, 1 valence electron. Potassium, can you guess it? 1 valence electron. And so that's another way that the periodic table is set up, is that elements within the same columns have the same number of valence electrons. And that is key for us. That's a very key thing to know when it comes to electron arrangement and the periodic table. One of the things that will do for us is it will help us to predict the charge on ions. We're going to use ions much more in just a few lectures, but I want to introduce the concept here. So remember how so far I've been talking about atoms being electrically neutral, where the number of protons is going to be equal to the number of electrons. The number of our plus charges equals the number of our minus charges. So they cancel out, and so the whole atom overall is neutral. So that's true for a neutral atom. If an atom happens to gain or lose 1 or more valence electrons, though, so if we have a situation now where the number of electrons does not equal the number of protons, that is now called an ion. So there's a charge imbalance there. So let's look at a couple quick examples of that. Thought I had this all set to go. There we go. Okay. So let's look at an example maybe of a sodium atom. So here's our nucleus. Sodium, right here, atomic number 11. And so remember, so we have our first shell, we have our second shell, we have our third shell. Actually, I want to draw this. Let's just do this. I want to make that a little bit smaller. Oh, here we go. Okay, so there's our nucleus. There's our first shell, our second shell, and our third shell. And so remember the order that electrons are going to fill in. We're going to have 2 electrons here in our first shell. We'll have 8 electrons here on our second shell. And sodium, atomic symbol Na, has its 11 protons, meaning a neutral sodium atom, 11 electrons. So we have 1 more. It's going to go out here on our third shell. Sodium, when it forms an ion, is going to lose that 1 valence electron on the outside. It's still going to have 11 protons. It's still sodium. But it's now going to only have 10 electrons because it's lost that third one. So we'll still have our 10 that were in here on the core, but now there's no electron on that third shell. And so where we were initially electrically neutral, no charge overall, now we have one additional proton than we do electrons, leading us to say that this sodium is going to have a 1+ charge. It's an ion. If we look at something like, oh, let's do chlorine. So here's a chlorine atom with its 17 protons, meaning it'll have 17 electrons in there, 2 on our first shell, 8 on our second, so we have 7 more. So there's our electron arrangement for chlorine. When chlorine forms an ion, it's still going to have its 17 protons, but chlorine is actually going to gain an electron now. And so now it has one additional electron than it does protons, meaning there's a charge of 1 negative. It's become a chlorine 1- ion. Positively charged ions are called cations. Negatively charged ions are called anions. Metals tend to lose electrons to become cations, and they'll lose as many as they need to empty out that valence shell. Nonmetals tend to gain electrons to become negatively charged anions with a full valence shell. The symbol for an ion includes the superscript that has the magnitude and the sign of the charge, just like we had right here. So our chlorine 1-. Main group elements will gain or lose electrons in very predictable ways. So everything here in our first column has 1 valence electron. It'll lose that valence electron to form a 1+ charge. All of our alkaline earth metals have 2 valence electrons. They'll tend to lose those to form a 2+ charge. Transition metals, not nearly so predictable. We'll talk in more detail about those in a few lectures. Aluminum will tend to lose its 3 valence electrons to form 3+ charges. Nonmetals tend to gain electrons, and again, they tend to do so in very predictable ways. Our halogens tend to gain 1 electron to form a 1- charge. Elements in group 6A tend to gain 2 electrons to form 2-. And atoms in group 5A tend to gain 3 electrons to form 3- anions. And so that concludes our look at electron arrangement. We're going to investigate ions much more deeply in a couple of lectures from now when we start to look at compounds and how they form. But I did want to introduce it now so that we can get used to the idea and looking at this balance between the number of protons and number of electrons in an atom. Thanks for watching.